In this unit, you learn how to answer the following question. How should packets from A reach B? Or in the multicast case, how should packets from A reach B, C, and perhaps other end hosts too? We started by studying 4 basic approaches used when routing unicast packets from one end host to another. First, we can flood packets over every link in the network. When a packet arrives to a router, it's replicated to all of the interfaces except the one it arrived on. This guarantees that a flooded packet will eventually traverse every link and will therefore reach any and every end host in the network. It's clearly very inefficient and expensive and needs to be coupled with a mechanism to prevent packets from looping forever. Flooding is used during times of uncertainty, when the topology is changing and we have no other way to be sure that we can reach every other host. For example, when OSPF routers are exchanging link state, they flood the link state packets throughout the OSPF domain, so the topology is known to every router, even when the topology has changed. Second, we can use source routing. In source routing, the source host puts into the header of every packet a list of hops the packet should traverse through the network. Clearly, this is possible if the end host knows the entire topology. Source routing means we don't need to exchange routing table information in the network. The routers don't need to contain a forwarding table at all. In fact, arguably, source routing is very much in keeping with the strong end-to-end principle. We shouldn't burden the network with having to know all the paths. But in practice, source routing is rarely used for a number of reasons. The biggest reason is security. Network operators don't like source routing because it requires them to expose the full topology of their network and open it up so end hosts can send packets wherever they want. The internet designers felt it was a worthwhile optimization for the routers to maintain a forwarding table to avoid having to distribute full up-to-date topology information to all the end hosts. Third, the routers can contain forwarding tables, which they clearly do today. Rather than relying on the source to provide the routing information, the forwarding table in the router contains the address of the destination and an indication of which interface to exit the router in order to move one step closer to the destination. Today, all Ethernet switches and internet routers use forwarding tables. The job of the routing algorithm is to populate the forwarding tables. Finally, you learned how unicast routing algorithms usually build a spanning tree with the destination at the root of the tree. It's a tree because we don't want loops. It's spanning because it provides a way for all source end hosts to reach a given destination. Generally speaking, routing algorithms used in the internet, such as OSPF and RIP, populate the forwarding tables so as to create a spanning tree across the network. Usually, the spanning tree we build is a minimum cost spanning tree, where we're trying to minimize the hop count, delay, or the distance traveled by packets.
You learned about 2 algorithms widely used to build forwarding tables in routers. The first is the Bellman-Ford algorithm, which is usually referred to as a distance vector algorithm. Each router constructs a vector of distances from itself to every other router in the network. In successive steps, the routers exchange their vectors so as to find the neighbor that is closest to each destination. After a number of iterations, equal to no more than the longest loop-free path in the topology, the algorithm will settle on a set of forwarding tables in each router that tells it how to route packets along the shortest path to every destination. The Bellman-Ford algorithm was the basis for RIP, the Routing Information Protocol, which is the first widely used routing algorithm in the internet. The good thing about RIP is that its algorithm is distributed. The routers work together to build a complete set of forwarding tables. This is important in the early days of the internet, when the routers were assumed to have very little computing power. However, RIP has many problems trying to converge on the right answer when the network topology is changing. We saw examples of the so-called counting to infinity problem, in which bad news travels slowly, and methods such as poison reverse to try and overcome it. Today, RIP is rarely used and has mostly been replaced by OSPF and an algorithm called ISIS. OSPF is based on the second algorithm, Dijkstra's shortest path first algorithm. Dijkstra's algorithm assumes that every router has the computational power to construct its own routing table, if it is given a complete topology. The routers learn the topology by exchanging link state information, basically a binary indication of which links are present and working. Once they have the topology, every router sets about calculating its own forwarding table so as to reach every other end host in the network. Dijkstra's algorithm is deceptively simple and fast. As a result, OSPF is very widely used in enterprises and college campuses today. In addition to RIP and OSPF, we studied 4 other aspects of routing. You learned how the internet uses hierarchical routing to break routing down into more manageable, locally controlled problems. Each autonomous system, or AS, chooses an interdomain routing algorithm to route packets inside its AS. For example, Stanford uses OSPF on campus. Every AS is required to use BGP, the Border Gateway Protocol, in order to exchange routing information with other ASs in the internet. BGP is the only sanctioned way to exchange routing information between autonomous systems in the internet today. Basically, every AS advertises to its neighbors the path packets will reach to every prefix in the internet. The path is the set of the ASs the packet will pass through along the way. We learned how every BGP router can use a locally defined policy to decide which route advertisement to accept and use to route packets. You also learned briefly about multicast routing. Multicast routing is an optimization added to a network to avoid the source having to send a packet multiple times to a set of destinations. Multicast was all the rage in the 1990s because it was thought that many applications, such as internet TV, would use multicast delivery. Although many multicast routing algorithms were invented and standardized, as you learned in the video, they are not widely used today. This is because most applications and services, such as video streaming, offer us the convenience of streaming us what we want, when we want, with a single unicast connection. Most of the time, there are far too few people watching the same video at the same time for it to be worth supporting the optimization in the network. Finally, you learned about the spanning tree protocol. This isn't actually an internet routing protocol per se, because it is a mechanism used by Ethernet networks to avoid creating routing loops. The spanning tree protocol allows a set of switches to construct a single spanning tree with one switch at the root in order to prevent packets from looping in the network.